don't open the camera. I know. So.
So you don't want to take a camera or a picture of the table?
Okay, cisp310. Oh, turn on the mic. Check the recorder. You don't want to record silence. Okay, something's working. You can never really quite tell whether it's recording my voice or just recording some random stuff. Okay, but let's just hope it's my voice. The only way we can confirm that is, yeah. All right, so this class is also going to get the practice exam, and I put the practice exam into subroutines. This is the actual final exam, which has more resemblance than the second exam from the previous semester, because I changed the ordering of the topics a little bit. So we'll take a look at the quote-unquote final exam of the previous semester. And obviously the length is not going to be this for your exam number 2, because your exam only has 80 minutes and the final exam has 120 minutes. So I will scale it back in terms of length of time, but in terms of the type of questions, it will be similar to these types of questions. As far as the rules are concerned, open book, open notes, no electronics, same thing, just like in exam 1. You can print anything you want and bring it with you. If you find textbooks that are useful, bring it with you. If you want to take screenshots of the videos, bring them with you if you think they're going to be useful. All right, so this is question number 1. Question number 1 is to find and fix all the problems of the assembly code implementation. So on the right-hand side, we have the assembly version, which is supposed to be problematic. And then on the left-hand side, we have the original C code. Do not assume the usual label definition of displacement or do not assume. Okay, so these labels basically become displacements to where things are. And this one does not involve structures, so you don't have to deal with the structure part. Correct code is marked wrong, but correct code that is marked wrong will also get points deducted. In other words, if some code is actually doing its job correctly, and somebody said, oh, this is wrong, we should have done it this way, that would be marked wrong as well. So be careful what you mark as incorrect. Rewriting the code from scratch is not going to receive any points. Because most people complain, oh, instead of finding these mistakes, it's quicker for me to rewrite the entire program to begin with. So that won't work. All right. This is string compare. This is one way to implement string compare. And on the right-hand side, we have the assembly version. So we want to find out, okay, do we have any problems with this code? Where do we start? Since everything makes use of the labels, we should start with the definition of the labels and make sure that these labels are correct. And right away, I think we should see something that is wrong already. What is wrong with this code? There's no old EBP. That's right. I start off with the return address having a displacement of 0 from where EBP points to. That is the first mistake. Okay. All right, so I have to find a way to display the correction along with the original text. And I know exactly what to do with this. So we'll download this first. Put it into the temp folder. And then reopen this using a really nifty program. It's called Xournal, Xournal. And the file is, where is it? Well, 2015, there we go. Okay, so it looks just like a PDF viewer, but you can also see all the other control items here because you can now mark up anything you want. So we'll zoom in a little bit. That might be a little too much, but it's okay. We got it. All right, so what we want to do is to insert some code over here. So I'm going to draw an arrow here. Oh, that's ugly. And then we'll put some text. And when we put in text, we say we want old EBP to be defined as 0. So this one, we want to redefine the 0 to old EBP plus 4. So that will fix the problem. Okay? So we want to cross out, let's see, we want to cross out this 0, so it becomes old EBP plus 4. Are there any questions about this correction? That the frame pointer EBP does not point to the return address, it is supposed to point to the saved version of EBP, and then the return address is 4 bytes after that. Is that okay or not? Okay. What about PA and PB? PA is defined to be return address plus 4, and then PB is PA plus 4. Is that okay? Okay. Why is it not plus 1, since we're dealing with characters? Because they're not actually characters. They're pointed to characters, and pointers are 32-bit wide. Okay, very good. So now that we have fixed the label, let's check the code. The entry code says push EBP, move EBP to ESP. Does that look right to you? We save EBP, and then we want to make a frame pointer out of the stack pointer. But what did I do instead? I overrode the stack pointer with the frame pointer. I did it exactly the opposite. Okay, so that's my second problem. Now, if you have any printout of usual way to do subroutines, you can just match the entry code and exit code and spot these problems. These are pretty much boilerplate kind of thing. So we go to font again, and there has to be a way to change the font size. Text font. We want to reduce it a little bit and choose maybe a mono. There we go. Let's give it a try. I think that's going to look better. We want to copy ESP to EBP, not the other way around. Is that okay?
Mm-hmm.
All right. Okay. Then we have a loop. Okay. So the loop is identified by L1, being the beginning of the loop, and then L2 being the exit point of the loop. Okay. So when you look at the loop, which is this while loop here, I'm going to use a highlighter. That's my highlighter. So L1 is indicating the point where I can go back to. So we want to make sure that the loop does jump back to the beginning. So we do have that. We also want to look at L2 and make sure this is my exit point, which means by this time I get out of the loop. So the exit point is coming out of here. This is one way to exit, and this is the other way to exit. So by looking at the use of label L1 and the unconditional branch to L1, I know this is the structure of a loop. Looking at the way I define L2, which is right after the unconditional branch, and looking at the conditional branches to L2, I kind of understand that L2 is intended as the exit label of this particular loop. Okay. So now we want to look at the condition of the loop, which is in C code. This is the part that we are looking at. And then we want to say, okay, is the assembly code actually doing that part? Let's look at asterisk P1, excuse me, asterisk PA, which is basically looking at what PA is pointing to and ask the question, is that not a null? Okay, that's what it's asking. And that part is implemented by this instruction and this instruction here. These two combined is attempting to do this one, because you can see a conditional branch to L2. Is that correct? Yep.
Can you do a move L2 or like a byte register?
Okay, that's the first indication that something is wrong. Okay, very good, good job. Okay, so the first thing is the move L instruction conflicts with the register AL, which is an 8-bit register. But if that is the problem, there are multiple ways to fix that problem. The first way to fix that problem is, we'll just change it to move B, because move B is a move byte, then everything is going to be good. But we are missing the point here. In the C code, what are we doing with PA? Are we comparing PA directly or not? If you look at the C code, okay, let me choose a different highlighter. If you look at this code here, what is it doing? If I add any more, it's going to be opaque and we won't be able to see anymore. Okay, so when we look at this code, asterisk PA, what is it exactly doing? Are we comparing the pointer to 0, or are we comparing something else to 0? We're comparing what it points to 0. Okay, very good. When you look at the assembly code, do you see any use of dereferencing? The clue that we are missing a dereference is we do not see any indirect operand, which is basically register in parentheses. So when you look at the move LPA in parentheses EVP, we are just comparing, we're moving the pointer, we're moving the least significant byte of the pointer to AL and comparing that to 0, which is not what we want to do. Yep.
So you want to move that to EAX instead?
We need to break it up into 2 steps, because we need to first put the pointer into a register, then we can use indirect to compare. Well, you can fix both instructions, or you can introduce one additional instruction. They will all be counted as correct, because I just need people to spot the problem and know what to do with it. Okay? If there are multiple ways to fix the problem, you can use any one of those ways to fix the problem. I'm going to choose 2 ways to fix. I'm going to choose the first way to fix the problem. So I'm going to change this AL here to EAX. In other words, all I'm doing with the first instruction is to copy the parameter, which is living on the stack, into a register. That's all this instruction is going to do. Then in the second instruction, I'm not comparing AL, which is the least significant A bit of EAX to 0. I'm going to do it indirect in the second instruction. So what I mean is this. I'm going to get rid of the AL here, and instead of doing the AL, I'm going to use indirect EAX. Okay? Any questions about this part? Yep.
Like for EAX, will that compare by just compare that to the least significant 8 bits of EAX, or?
Are you talking about compare byte $0 to paren EAX?
Oh, never mind,
Because it's comparing a byte. Okay, the compare byte instruction does not have a problem, because it's not really comparing to EAX, it's comparing to the byte that EAX points to. And that's why we have the parentheses surrounding EAX. It turns it into an indirect operand. Are we doing okay with this one? Yes? Okay? All right. Is the JNZ instruction correct? In other words, we are jumping if it is not 0. Is the polarity of the conditional branch correct? Nope, it is not correct, because in this case, it is the same thing as saying, oh, if PA points to a non-null character, let's get out of the loop. That's not what we want to do. We want to get out of the loop if PA points to a null character. So it becomes JZ. Yep, exactly. So we cross out the JNZ, cross it out, and turn it into a JZ. The polarity of the jump is the issue with this one. All right, so now that we got that part done, let's check on the second part. The second part is comparing what P8 points to with what PB points to. If they are the same, we stay in the loop. The other way to look at this is if the byte pointed to by PA is different from the byte pointed to by PB, then it's time to exit the loop. Okay, that's the other way to look at this. Is that correct? The code right here, is this doing what it is supposed to do? Not even close, is it? It's not even close, because what are we actually comparing in this case? Assuming EAX is PA at this point, what are we comparing with the compare byte instruction?
like just
We're comparing the least significant byte of a pointer with the least significant byte of another pointer. Has nothing to do with what the pointers point to. Okay, so we have a huge problem here, because it's not going to work. So let's cross this out and figure out how to fix this code. Okay, so this has to go. This has to go. Instead, we need several instructions in this case. So the replacement is going to be several instructions. Okay, we already have PA in EAX. Okay, so let's kind of keep that, okay, because it's going to be handy. So what we need to do now is to move PB, EBP, which is the other pointer, into E. I don't want to use EBX because EBX, EBP, there are several registers where they are supposed to be preserved. EDX is safe to use. I'm going to use EDX here. So now I have PA in EAX, PB in EDX. I really want to do this, compare byte, whatever EAX points to with whatever EBX points to. I cannot do this. Why not? There's a restriction.
2 indirects.
2 memory operands,
Right.
okay? But you're correct, okay? The 2 indirect operand is the issue but the more general restriction is you can only have up to 1 memory operand. And this time we have 2, okay? So we cannot do this. Oh, it's EDX by the way, but the problem is the same, okay? All right, so since we cannot do this, what are we gonna do with this? Well, we have to go through a particular register to do the compare. So we're going to do a move byte. You can pick one or the other one, doesn't matter which one you pick. I'll just pick A here, okay? This is fine, okay? There's no problem with using EAX as the first operand and then use AL as the second operand in the first in the same instruction. There's no problem with this, okay? But what this is going to do is AL eventually stores whatever byte that EAX originally points to. So now I can use AL for the comparison that follows this. So now that I have one of the bytes stored in the register, the other one is still pointed to by EDX, it's okay. I can now do a compare byte, sorry. So I can now do a compare byte. The order is not important in this case because we're only checking for equality versus inequality. We're not trying to see which one is larger. So you technically do not need to specify the order. So this works just as well as flipping the 2 operands because we just need to see whether they are the same or not. So this will finish the actual comparison. After this, we have a JZ. Is that correct? Now JZ to L2, let me just point out which part I'm talking about here. This part here. JZ to L2 means that if the bytes pointed to by PA and pointed to by PB, if they are the same, let's get out of the loop. Is that the intent of the C code? That's opposite to the intent of the C code. So that means the JZ instruction should be a JNZ instruction. Very good. Okay. So we'll cross that out and replace it with JNZ. There we go. All right. Next one is, okay, if we do not end up branching out of the loop, we add one to PA and we add one to PB. Are those 2 instructions correct? Incrementing just the pointers. They're fine, okay? Add long is important, so we want to check what? We want to check the width of the operation first. 32-bit add is good. We want to check whether we are adding to the right thing. We are adding one to the parameters. That's correct as well. Okay, that's all good. Okay, so we can either close the door or we can tell those people to.
Ooh, I like that plan.
Let's go ahead and ruin their day.
Okay, excuse me, but the room is really hot, so we have to open the door, but we can hear you from the inside the room. Thank you.
So to go.
I guess you guys heard that too.
Mic was on.
All right.
Suppose we could have the door open now.
Well, we'll give them a few minutes to disperse. But I think they're not being loud anymore. So let me open the door. Is that okay or not? Should I go back outside? Okay. So that part is okay, adding one to the pointer's PA is good, adding one to the pointer PB is okay. Unconditional branch back to the beginning of the loop is okay. Okay, so now we are down to the return instruction here. We are trying to return the difference between what PA points to and what PB points to. Okay, so here we have an interesting issue. So we'll deal with one thing at a time, okay? You can see that at L2, which is the exit point of the loop, I start with a JNZ instruction, okay? Would that be correct or not? Given that we have fixed the code as it is now, having the JNZ instruction right at L2, is this okay? We look at this one instruction, and then we say, okay, what is L3 and what is not at L3? In other words, the question is, by the time we get to L2, what does it mean when the Z flag is set? What does it mean when the Z flag is cleared?
Z flag is set and the two characters that are being pointed to are the same. So then it would be
Okay.
Isn't there no way to know for sure? Just we have two X's.
Well, if it is, if the Z flag is set, that means we know we got out because of the JZ instruction, which means we found a null character. Okay? Does that make any sense? Okay, so we find that PA points to a null character. That's the only time when the Z flag is going to be set. If the Z flag is reset or cleared, that means we got out because of the second instruction, the JNZ instruction, which means we found that the 2 bytes, one pointed by PA, the other one pointed to by PB, they are different. Okay? So this JNZ instruction is going to L3, where we actually do the subtraction. Okay? And the subtraction is doing something with ECX, and ECX was never used anywhere earlier, so that's definitely going to be a problem. But let's not worry about that part here. This is the subtraction that actually does the computation, which is the end for the end result of this whole thing. Would that be correct? And then the alternative, what is the alternative here? The alternative is putting a 0 into EAX and then branch to L4, and that's in the case when Z is actually set. When we branch to L4, it pushes a -1 onto the stack, and then we do something with a label, register AL. Well, looks like that whole code is not working based on how we fix this code here. Okay, so in this case, because of the way we fix the code, this part here is not going to work at all. Are we doing okay so far with that? Okay. So assuming this entire part is no good, okay, so we cross out everything down to including L4. So now we can reuse all these labels. Okay. The purpose of this code right after the loop is to return whatever PA points to minus whatever PB points to. So now the question is, how do we implement that? Even assuming none of the registers has the pointers. Okay, so how do we do this? Okay, let's start with some. Yeah, go ahead.
Tak, so this wouldn't be considered rewriting the code, which you said we can't do?
Well, but if the original code is not working, then you don't have a choice.
Yeah, I guess it's half of it.
Well, the majority of it.
Yeah, majority.
Okay, so we know we need to use PA. Okay, so let's put that into a register. And we also know that we are not really that interested in the pointer itself. We are much more interested in whatever it points to. So let's do that indirect as well. So now AL is whatever character PA points to. Yes?
Could you do the same thing with like PB and EBX or?
Yeah, we can do the same thing with that one. But once we have one in a register, the other one doesn't need to be in register anymore. So now we can just move PB, EBP into EDX. Okay, just into another register. And we want to do the subtraction. We want to find out what is the difference between these two numbers. So the subtraction is subtracting the second operand, subtracting the first operand from the second one. So it has to be kind of in the opposite order. So we have to specify EDX in parentheses, which is indirect, and then AL as the second component. Are we doing okay so far? Yep.
Do we have used a different register other than AL and JZ, the first branch, so we can keep the content of EAX and EDX and reuse them down there?
But we don't have to reuse it, that's the point.
We don't have.
We do not have to reuse it. Okay? Okay, so let's look at these 4 instructions. The first instruction just put the pointer PA into EAX. And then the second instruction immediately makes use of EAX and say, okay, what is the byte pointed to by PA? And store that into register AL. So AL is the actual byte that I want to use as a part of the subtraction. Is that okay? That will be the left-hand side of the subtraction. Is that part okay? In other words, if I were to draw a line connecting the concept, okay, let me see if I can pick this one, a different color. So I guess it makes it kind of hard to see because the pointer itself becomes that color. Okay, so this one is now in AL. Is that okay? I copy PA, which is a pointer, into EAX, and then I use indirect EAX and store that result into AL. Is that part okay? All right. And PB is stored into EDX, so indirect EDX is actually whatever PB points to. So this entire thing, including the dereference, is referring to this, the first operand of the subtract byte instruction refers to dereference PB. Is that part okay? All right, so we do the subtraction just fine. And after the subtraction, the difference is already stored in AL, which is a part of EAX, which is how we return a value in assembly language. So it seems like everything is good, except there's one problem. How wide is the result here? The C subroutine has a return type of an int, and int is how wide? 32-bit wide. And yet, when we compute the result in the register, it is only how wide? It's only 8-bit wide, okay? So now we have an 8-bit number that is the actual result. It can be positive, it can be negative, because depending on which character is larger, this can be positive or negative. And we want to, what we call sign extended. In other words, we want to look at an 8-bit number and say, okay, just extend the sign to a 32-bit number. Are we, okay, let's do it on a piece of paper first. So let's switch to paper. All right, how do we represent 1 as an 8-bit number? Okay. 0, 0, 0, 0, 0, 0, 0, 1. That's how we represent, whoops, I guess we have a clipping problem. There we go. This is 1 represented as an 8-bit number. How do we represent 1 as a 32-bit number?
Add a bunch more zeros.
Yep, just pad all 24 bits to the left with 1s. Well, that's an easy one. 1, 2, 3, 4, 1, 2, 3, 4, blah, 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 0, 0, 0, 0. Okay, so we just have 24, we just have to pad 24 zeros. But that's because 1 is non-negative. How do we represent -1 as an 8-bit number? We use 2's complement, but when we apply 2's complement to 0, 0, 0, 0, 0, 0, 0, 1, what do we get? We get 1, 1, 1, 1, 1, 1, 1, 1. Okay, very good. So that means 1, 1, 1, 1, 1, 1, 1, 1. is the representation of -1, the value, in 8 bits.
Mhm.
How do we represent -1 using 32 bits? Exactly, we have to pad 24 ones. So we have to pad all these extra ones to the left-hand side in order to preserve the value of -1. So that means how we pad the other 24 bits depends a lot on the result of the subtraction. If the result of the subtraction is negative, we want to pad ones. If the result of the subtraction is non-negative, we want to pad zeros. Okay? All right. So switching back to the code here, knowing that that's what we want to accomplish, what do we need to do? I think we need a conditional branch here because we have to differentiate between the case where we have to pad zeros and the case where we have to pad ones. Now, which one you want to use for branching away doesn't really matter because we can always switch the branches and what they do. But what flag do we need to look at in order to determine?
Sign flag.
Hmm?
Sign flag.
The sign flag, very good. Okay, so
JS.
it's either JS or JNS, okay? You pick one or the other, it doesn't really matter, okay? I'm just going to say JS here. So we branch when the sign flag is set to a particular label. I don't even care which one, let's say L1. But that means at this point, it is the sign flag is a 0. If the sign flag is a 0, it is non-negative, and we have to pad zeros. Is that making any sense? So we want to pad zeros here. I'm going to do this little trick here. Instead of padding zeros, I'm just going to push constant 0 on the stack. But when I push constant 0 on the stack, I'm pushing 32 bits of zeros on the stack. And I'm just going to let it sit on the stack. And branch, do an unconditional branch to another label. We'll just call that, oh, I cannot use these labels, can I? Because they were used before. So we can use L3 and L4 here. All right. So at this point, I can define L3. And L3 means if the sign flag is a 1, which means we have a negative result. So we're going to push -1 on the stack. But -1 is just a convenient way to specify 1, 1, 1, 1, 1, 1, 1, 1, 32 ones as a binary number. Because the representation of the value -1 is 32 ones when we use a signed 32-bit representation for -1. Is that okay?
Mhm.
So we're basically pushing 32 ones, on the stack as a 32-bit number, and now we are down to L4 as a label. In other words, the two branches are merging at L4 because there's only one little thing we have to do at L4, which is move byte. Which register stored the actual difference? The 8-bit difference is stored in which register? In AL. Okay, so we're going to move %AL to whatever the stack pointer points to. Hold on a second here. What is the definition of the stack pointer? What does it point to?
Whatever was pushed latest.
Whatever was pushed last, right? And it will be the lowest byte of whatever we push last if we push a multi-byte thing on the stack. And what did we push on the stack from either branch? -1 or 0 as a 32-bit number, okay? So I'm overwriting just the least significant byte with the actual result that was computed as an 8-bit thing. So that's how we do the extension. The result is on the stack itself. So when this is all done, we do a pop L into EAX. So now EAX would actually contain the result that we want. And that will conclude the actual computation of the return value. When we're done with the return value, we look at the exit code here and say, okay, does that look right to you? Are we copying the frame pointer back to the stack pointer? That's good, not a problem. We pop EBP, that's good too. So are we all done? Or are we missing something? Yep, we're missing the return instruction here. So here's a return instruction. There we go. Most people miss that return instruction at the end in this question. So is that okay so far with this question? So remember, I will scale back in terms of complexity, but this is the kind of question that it will ask. Give you the C code, give you the incorrect assembly code, and then you have to spot the problems and fix it. But probably I won't do anything quite as elaborated as this one, which is sign extension.
When is the exam for this class?
1 week from today.
So you have 2 exams pretty much in the same day.
For some of you, yes, unfortunately. I cannot space it out. We don't have the time to space it out anymore.
Just call that an exam and go.
But this is a good warm up for the final
For the
exam.
final, right.
Yep. Okay, so this is the other type of question that I can ask you is to decompile a program. Okay, this is basically decompiling a program, which means I want you to look at the C code. I want you to give me the C code. So if you read the text of question number 2, it says, reverse the following assembly code into C. Assume all labels are properly defined here. Okay, so in other words, you can assume ODPP, return address, the individual parts they're all correctly defined. The C version must have the proper return type. Okay, let me scroll a little bit here. Oh, there we go. So the C version must have the proper return type, parameters, and their types, the parameter types. Yep.
Will we be penalized if we convert it into C++?
I don't see how it would make a difference.
Okay.
Because the only difference, or one of the major differences between C and C++ is C++ has objects, and we have not even gone over structures, which is the predecessor of classes. So I don't really see how it will actually make any difference. The only part that can potentially make a difference is passive by reference, where the notation is different between C and C++.
And in C it's the parentheses, but C++ has the ampersand?
In C, you cannot pass by reference. You can only pass by pointer. So the dereference is explicit in your code. In C++, you can pass by reference, which means you don't have to do the dereference manually. Okay. In the case of type cannot be fully resolved, just pick one of the possible types. Okay. So let's take a look at this code here. It's really solving a puzzle. This code is not really that long, but we want to see, okay, but how do we do this? Okay, let's start with a few things. So let's just say that we don't know what type it is returning. Okay, so we say unknown return type. We know the subroutine is called X. Now we want to see, okay, does it have parameters? If you look at the label definition, does it suggest that there are parameters? There are things on top of the return address, and those are our parameters. In what order? What is our first parameter? PA is the first parameter, okay, and what is my second parameter? N is our second parameter, okay, very good. We don't quite know the exact type of these things, but we know they are 32 bits, okay, so we just say 32-bit wide and 32-bit wide as well here. We don't really know exactly how wide N is, so we will just leave it unknown, just unknown here. There we go. All right. Then we go into the definition of the actual subroutine. Do we have any local variables?
L.
L is a local variable. What gives that away? It's a -4. It is on the negative side of ODPP, so that's where local variables are stored. So we know that L is a local variable. We don't know exactly what the type is, but we do know the width of that operand, of that local variable. What is the width of L? 32-bit wide. Okay, so we know it's 32-bit wide something. Can be a pointer, can be integer, can be an unsigned. We don't quite know exactly what it is. Yep.
The ones on the positive side of EBP are the parameters? Okay.
Correct. Now, just to explain that part, okay, because when you look at a stack or the construction of a frame on a stack, okay, so let's say this is memory space, and I always use this convention: high memory goes to top, and low memory goes to the bottom. Okay, the stack grows lower and lower. Okay, so that means the parameters have to be pushed first before the call instruction itself. So we have potentially or optional parameters, and then the call itself is going to push the return address on the stack. Does that make any sense? This is all done by the caller. Okay, this is before the subroutine has control. When the subroutine has control, this is what the stack looks like. The return address is the last thing that it was pushed on the stack. The convention that we use in this class is we push EBP right away. So that means old EBP is going to take up this space here. Old EBP is here. So where are we going to put the local variables? Below that. So that's why the local variables, local vars, are always going to be here. The frame pointer, EBP, is initialized, so it's always pointing to old EBP. So that is a universal structure of all core frames, and that's how we can look at the definition of the labels, and you can easily tell, okay, this is a parameter, that is a local variable. Is that okay? Okay. So now that we have figured out, the kind of how we use the data space, now we have to look at the code and find out, okay, what are we doing with this code? Push EBP is correct. The assembly code has to be correct, okay? Because if I give you incorrect assembly code, you cannot translate that into C code. You cannot do the one-to-one equivalence, which is also going to be helpful. I'm not sure how many people did that last year, is to use this at least as a template to fix some of the problems of the previous program. Because this shows you what, at least the entry code and the exit code and how we define the labels, this one is correct already. So if you compare this code with the previous code, it will at least help you with spotting certain problems, okay? All right. So the first thing we actually do here is to put a 0 into L, okay? So we say L equals to 0. We cannot conclude whether L is a pointer or not in this case, because a null pointer looks just like this, okay? A null pointer is a 0. But that's okay. We don't need to make that determination right away. So the next thing we notice is we have some kind of a structure here. We have L1 over here, which doesn't seem to do anything. So next time when you see a label before any branch back to the label, it is indicating we have a loop, exactly, okay? So either we have a while loop or we have a do while loop. In this case, we know we have a while loop because we can see that there's an unconditional branch at the bottom of this code to go back to the beginning. So whenever you see a label here, you have an unconditional branch back up, and then you have an exit label right after the unconditional branch. That's an indication that we have a while loop, a pre-checking loop. Okay, so when we have a pre-checking loop, I will just go ahead and write the structure of a pre-checking loop, because that's how I can see that how label L1 and label L2 are indicating. Cool. So let's go into the condition here. The first way to get out of the loop is when n compared to 0 ends up with a 0 flag. What is the shorter way to say that?
N is equivalent to
When
0.
n is 0, okay? But wait, we're exiting when n is 0, so that means when do we stay in the loop? Because in the while loop, we specify the condition to stay in the loop.
So while n.
While n, okay? N by itself is fine, okay? All right, so if that doesn't get us out of the loop, we have a second reason to get out of the loop. Okay, if I have multiple reasons to get out of the loop, that means what logical operator should I use to specify the while condition? Should I use conjunction or disjunction? Okay, let's think about it one more time, okay? Maybe it's exclusive or implication.
I must be reading this wrong.
Okay, but
What's
let's just think about it one more time, okay? In the assembly code, we have one reason to get out of the loop, which is the 2 lines right below L1, right? But we do have a second reason to get out of the loop, which is the three lines right after that. So we have multiple reasons to get out of the loop, which means to stay in the loop, the flip side of all of the conditions have to be true at the same time. So we have conjunction in the while loop itself. Okay? All right, so n is one of the reasons that we need to stay in the loop. What is the other reason? What are these instructions doing, these 3? The first instruction is moving PA into EAX. Yep, go ahead.
Sorry to pull you back a little bit. Let's go 2 lines above L1. Why did we add log L to ESP?
To allocate the space. If we don't do this, then ESP will still be pointing to old EBP,
Yeah.
and we won't have the space allocated for the local variable.
Oh, so that belongs to the instruction before, not the one after that. The continuity of the one, no?
Okay, let me see if I understand which instruction you're talking about. I think you're talking about this instruction, right?
That one, yes.
Okay, so this instruction is changing the stack pointer because at this point, I have only allocated and used the space up to the old EBP, right? The stack pointer is still pointing to old EBP. If I want to use the 4 bytes below this as my local variable, I better move the stack pointer lower so that any additional call or any other use of the stack won't trash local variable L.
But that would imply sub L, not add L. If you look at the.
What is the definition of L? What is the actual value of label L?
4.
Nope.
It's not 4.
Nope. It's -4. It's ODBP minus 4, and ODBP is 0. 0 minus 4 is -4. So I'm adding -4 to ESP, which means I'm allocating 4 bytes on the stack. Okay, but it's good to check, yes. Very good. All right, so getting back to the code that we are dealing with here, and I think it does let me continue typing.
I've got doubts.
There we go. Yay. Okay, so we can get back to here and look at the second condition to stay in the loop. Okay, but the assembly code presents the reason to get out of the loop. But let's find out what is the reason to get out of the loop here. We have seen this already. Okay? We are moving along, which means 32-bit wide move, PA into EAX. So EAX now has the same thing as the parameter PA. But what am I doing to EAX? I'm not comparing EAX to 0. What am I actually comparing? What EAX points to, okay? Which is what PA points to, right? So I'm comparing what PA points to 0, and it's a byte compare because we can see it's a CMPB, a compare byte instruction. So how do we, and if they are the same, I get out, which basically means if PA points to a 0 byte, a byte of 0, we get out of the loop. How do we stay in the loop? When it's non-zero. And how do you say when, how do you say PA points to something that is non-zero? How about just that? Would that do? Yep, okay. All right, so now we're in the loop, which is starting with the add out instruction here. Is there anything suspicious with the add out instruction? We're adding 1 to local variable L. I think that's about it. Add L, $1, oops. That's C code. There we go. That's the C code, plus L, or if you like, L equals L plus 1, L plus equal to 1, they're all the same. What about the next instruction? What is it doing with N?
Decrementing.
Just decrement, okay? So minus minus N minus equal 1, N equals N minus 1, they will all do the same thing. Okay, nothing after that because the unconditional branch is an indicator that we have hit the end of a while loop. That's good. All right, after we get out of the loop, what do we do after L2? We move L into EAX, and then we have the usual exit code, which is copying the EBP into ESP, pop EBP, and then return. So that means, what are we actually returning? L, okay. So we return L here. All right, so we pretty much have everything that we need except for the types of stuff that we're returning. Okay, so let's deal with PA first.
Seems to be a
Quite
pointer to a
obviously, the
chart.
PA is some kind of a pointer because we dereference it. And after we dereference, we use compare byte, which indicates that it is pointing to some kind of char, okay? So we just say that this is that, okay? If you say unsigned char, I will count it as correct as well, because there's no indication whatsoever in the code whether the charge, whether it's signed or unsigned, because there's no JG to indicate it is signed, there's no JB to indicate it is unsigned. So without any indication, just pick one, they will both be considered correct. What about N? Did we ever do any dereferencing with N? Nope. So it's going to be, you can use a variety of things. You can say int, you can say unsigned, they will all be considered correct. But whatever you use, and then what about L? We initialize it to 0, and then we return it in, as this part of the program. Yeah, probably just an integer. It can be signed, it can be unsigned. Once again, I did not have anything to indicate whether it should be signed or not, so we can pick either one. And the same thing over here, because that should have the same type as L, because I'm returning L itself. So what I will look for is the type of this local variable should match the type of this thing here. But N really does not, can be either one. Are we doing okay so far with this code? So once again, you do have flexibility. This is one possible way. The wiggle room has to do with the types of the return type, the type of the parameters, and also the type of the local variable. And then how you want to express the condition is up to you. Because you can always use the longer way to express these expressions. So if you want the longer way to do this, you can say this is not 0. And also, this is not 0, which is implicit. Okay, but that will be considered exactly the same thing. Once again, with these, there are so many ways to do it. You can say L equals L plus 1. You can also say, L plus equal to 1. You can also use L plus plus, because whether you're doing pre-decrement or pre-increment or post-increment would not make a difference here. Is that okay? All right, so that's the second question. And moving on to the third question. The third question is exactly the opposite of the first one. Implement the following subroutine in assembly using the same recursive logic. Yep.
I'm sorry to play again. There was no need to increment the ESP because we didn't push or pop anything into it.
You don't pop anything.
Was that?
Say that one more time.
The highlighted line?
The highlighted line here?
We didn't use ESP at all.
But it's good practice, just in case we did.
What if you have an interrupt? Remember, anything below what the stack pointer points to can be corrupted. The stack pointer marks what is the last byte that is a part of the stack. But anything that is not a part of the stack, from the perspective of your code, can be modified without you knowing it. So if you want to use that 4 bytes below where EBP points to, you better move the stack pointer to that point, because otherwise, things can happen to those 4 bytes. We haven't really talked about interrupts yet, but that's what we need to do. Okay, is to make sure that whatever you need to use is above or at where ESP points to. Okay. Question number 3. Question number 3 is just implementing the subroutine. I chose to use a ternary operator here. Implement the following subroutine in assembly using the same recursive logic. And the instruction, come on, scroll. Make sure the subroutine is safely callable from C from the perspective of how you use the registers. If you use EBX, you better save and restore that. You have to save and restore EBP and that sort of thing. And there's no waste of stack space, which means after you make a call, you're supposed to reclaim the space used by the parameters. Write the entire content of the file containing the definition of the subroutine in assembly. Okay, so let's go ahead and do this one. Dot global str chr. Okay, just to export the label. And then we want to define the labels. I would define the labels. If you can keep track of everything without the labels, that's okay too. I would not recommend it. So we have the usual typical structure of the stack. Then we have the first parameter and then the second parameter. Oops, almost got this wrong. Okay, we do not have any local variables, so that should be it. And then we have the label of the subroutine and the return as the last instruction. Now obviously when you do this on a piece of paper, you cannot do it the same way that I do. So you just put the return all the way down at the bottom. Okay? And then we have the usual stuff. Now if you want to use the insert thing because you forgot something, that works too. So that's one flexibility that you have when you're working on a piece of paper. So now we have push EBP, move ESP to EBP, and then the exit code is pop, move first, move EBP to ESP, pop EBP. Okay. So now that we have these things in place, we can actually go ahead and specify the logic. The ternary operator is really the same thing as a conditional statement. So in this case, we have a nested ternary operator, which means we have a nested statement here. So we still want to do things one at a time. The first thing we do is to compare whatever S as a pointer points to against C. Now you can see that one is a pointer to a character, the other one is an integer. So when you compare these, you're basically just comparing characters. Okay? So what we'll do is to specify the logic to do that. So we copy the pointer into a register first. Now this is going to be very typical. When you use a pointer, when you need to dereference a pointer, you have to get a pointer into a register first. Then you can do the dereference. Okay, so now we have this. We'll go ahead and put that into AL. And then we'll do a compare. Oops, this is wrong. This is a move long. Should be just a move byte. Then we have a move compare byte to C. Okay, so we have C EBP here, and AL is already having the character pointed to by S. Okay. After the compare, we usually have a conditional branch. In this case, I'm going to use the same structure as a conditional statement, which means if they do not equal, I go to the else case, which is representing the second part here. So the else is going to be defined down here somewhere. Now once again, when you write code like this and you can't insert code like I can do with an editor, so what you do is you can do the insert and just say, okay, this chunk of code goes between these two lines of code. Okay. So if it is non-zero, okay, oops, I take it back, else is J and Z for not equal to. In this case, I just want to return the pointer S itself. Well, that's pretty easy. Copy that to EAX and jump to a label that marks the end of the subroutine. So I just say end, and we'll define end, at the end here. The else is another conditional statement, but this time I'm comparing whatever S points to just a 0, and I'm just going to be lazy here. If you want to copy the pointer again, that's okay. But I already know that AL is whatever S points to, so I can just do a compare byte of 0 against AL in this case. And then J and Z to else, because it is the else of the else. Yep, go ahead.
Is that the right thing to do, moving ESP into EBP?
ESP to EBP, yeah, it is correct.
I thought that's exactly what you corrected on question 1.
Well, let's check. In question number 1, originally it was moving EBP to ESP, which is incorrect. I fixed it to ESP to EBP.
Okay.
Getting back to. It lost the focus. That's okay. We can still do it. Okay, so we are at this point here. Okay, we are checking for the no character over here. Okay, if it is the no character, I just want to return 0 as a result. Okay, so that means if I do not do the conditional branch to else, I just want a 0 as the result. Move a 0 into EAX, jump to the end. The else, which is representing the recursive call, is okay. We just have to call string char again. Okay. In order to call string char, how do we push the parameters? What is the ordering of pushing the parameters?
Even S plus one.
We push C first, and then we push S plus 1. Okay, very good. So we push C first. Down here. That's fairly easy to do. That will do it. So in the exam, we can use cisp instructions. You don't have to adhere to the RISC philosophy, because this is a lot easier, trust me. Okay, that takes care of the second parameter. What about the first parameter, S plus 1? What do we do about pushing S plus 1 on the stack? You can put it into a register first. There are several ways to do it. You can put it into a register, add 1 to the register, push the register.
Or you can just like add 1 to the value on the.
That would not be quote unquote the correct way to do it, even though it is going to be fine in this case. What I think what you're suggesting is adding 1 to S and then push S on the stack. Is that right? But the actual C code does not change the parameter S. So even though it's not wrong because the code does not make use of S after this point, it would still not be a preferred way to do it because we don't want to change the parameter itself. The other way to do this is to push it on the stack first and then add 1 to whatever the stack pointer points to, which looks like this. So we're going to push S not what it points to, because this time S plus 1 is referring to the pointer itself and not what the pointer points to. So we are actually pushing S on the stack, but we have to add 1 to whatever is already just pushed on the stack. But I can do this. Okay, let me just scroll up here. That would do it, because I just push S itself on the stack, and then I say, oh wait, add 1 to what I just pushed. Because in parentheses ESP is saying, okay, what the stack pointer points to, which is what I just pushed. Is that okay? So now we have both parameters on the stack. The only thing left to do is to make the call to strchr, string char. And when string char returns, there's only one thing that we need to do, which is reclaiming the 8 bytes used by the parameters. And that's it. Because the return value of that invocation is already in EAX, which is what I'm supposed to use to return my value. So it's already at the right place. Really good. Okay? So if that is the case, I just have to define n as a label here, because the other branches have to merge at this point so that we get to the exit code together, and that's it. That's one way to do it. There are definitely more than one ways to implement this subroutine, but this is just one way to do it. Are we okay with this code? Okay, just scroll back to the question itself. Any questions about this particular question? No questions? Well, if you do have questions later on, just let me know. We will get back to this. Okay, question number 4 is to use the function declaration of question number 3. Implement the following code fragment in assembly language. You may assume the following local variable / parameter declarations. So you can assume stuff is a const char pointer. You can assume wanted is a char pointer, and you can assume n is a integer. So I just want to implement this code here, which is a fragment. Okay. Do you guys want to do this, or do you want to see what question number 5 is? Because this one is kind of the same thing as the previous one, minus you don't have to set up the stack and clean up the stack because it's not a full subroutine. I would check on question number 5 first. Question number 5 is observe the following C code, C function. The following is a faulty assembly language implementation, but this time I don't want you to fix the problem. This time I want you to figure out specific cases where this code appears to work. And I want you to figure out the cases where it's not going to work, and other cases where the symptom will show up. Okay? So I just want you to understand what the question is asking first before we start to tackle this problem. So the first part is, you may assume the following code fragment is used to test the code. We have 3 variables, x, y, and z. X is initialized to a particular value, which you have to fill in. Y is going to be initialized to another value, but you have to fill in as well. Z is going to store the return value of compare swap with the address of x as the first parameter and the address of y as the second parameter. So I want you to, these are the format of the questions, of what you want to specify. Identify a case where this code does work correctly, or does appear to work correctly. What are the test cases? What is the initial value of x? What is the initial value of y? What is the result value in x? What is the result value in y? And what is z, which is reflecting the return value of the subroutine. But this is the case, it's a false positive because the code is actually incorrect, but it is masked. It is not, it appears to work correctly. In the second part, I want you to identify a case where this code does not work correctly. The symptom does show up. What value do you use in x to test this code? What value do you use in y to test this code? What is the result in x? What is the result in y? What is the result in z? And explain why this symptom happens. Identify the instructions at fault, but there's no need to fix it. Okay, so first of all, do we understand what the question is about? Yep.
You're basically asking how do you break this program in
How do you
expected way.
Correct. Knowing the source code, how do you test this code where you have a false positive, where it seems to work correctly, and then how do you actually have one test case where the code is going to break? So the first thing you do have to do, you do have to look at the code and see what problem it has, but then you have to go one step beyond that and say, okay, I know what the problem is, but instead of fixing the problem in the source code, now you have to say, okay, so if this is the code written by somebody else, why would that person not catch this? Okay, what test cases is not going to catch this particular fault? And then you have to think about, okay, but what other test cases can we use to actually find this fault? So I think going over this question is better than question number 4, because question number 4 is kind of like question number 3, it's not really that much different. Okay, so we'll go back to this code and take a look at both the C code and the assembly code. So this is the C code. We just have to understand the C code first, and then we'll go to the assembly code. The types are important. Int, okay? They're signed. Because signed is important when you're comparing for ordering. The greater than, as opposed to equal to or not equal to. Greater than means you have to use the correct branches, the correct flags. So if whatever PA points to is greater than whatever PB points to, we will perform the actual swap, and then we will also put a 1 into T as the return value. If whatever PA points to is less than or equal to whatever PB points to, then we return a value of 0, and we do not do any exchange. Are there any questions about the effect of this code? Is that okay or not? Okay, so we basically want to maintain the order of whatever PA points to and whatever PB points to. The end result is we want whatever PA points to be less than or equal to whatever PB wants to. And then the return value itself is indicating whether a swap actually took place or not. Is that okay? All right. So understanding that is what the C code is doing. Now we look at the assembly code and say, okay, is that really doing what it's supposed to? So we go through the usual stuff, push EBP, move L ESP to EBP, that's the correct entry code. Adding the displacement of the local variable to ESP, that will reserve the stack space. So that part is all good, that's all good. The exit code is moving EBP into ESP, pop EBP and return. You can compare the entry code and the exit code with earlier code, that's okay, that's not a problem. So whatever we are really doing is in between here. And right away, I think most people should see that, hey, there's a problem here. The conditional branch has a problem. Okay, we are moving PA into EAX, and then we move indirect EAX into EAX. That's just getting whatever PA points to and store it into EAX so we can compare later on. We do the same thing with PB and then ECX. So EAX and ECX will represent whatever PA and whatever PB points to, and then we perform the comparison. We are supposed to use the opposite of whatever this comparison is to go to the else branch. This is saying PA is whatever PA points to is greater than whatever PB points to. The opposite of that is, yeah, go ahead.
Never mind that.
Okay, so the opposite of this is whatever PA points to is less than or equal to whatever PB points to. That's when we get to the else branch. If you look at the assembly code, is that what we're doing? We branch to L1, which is the else code here, whenever whatever EAX is below EBX. It has two flaws in it. The first flaw is signed versus unsigned. The second flaw is what if they are the same. Okay, so there are two flaws here. So we'll just go ahead and highlight this instruction first because I know it has a problem. Okay? But what is the effect of this problem? Sometimes this program will still do what it is supposed to do correctly, and other times it would fail. Yep.
Like if it's equal, it'll continue to fall through and then continue on.
It doesn't do the branch correctly, but only in some cases. Under what circumstances is JB is going to behave differently compared to JL? That's just signed versus unsigned. Yep.
Isn't JB the borrow flag?
B is the borrow flag or the carry flag. It's the same. That's for unsigned comparison. L, on the other hand, is for signed comparison. So when does it make a difference whether a number is signed or not? Okay, what about 0 and 1? If I compare 1 and 0, would it make any difference whether I use the B flag or whether I use the L flag? Nope, it would not make any difference. So when is it going to make a difference? Negative numbers, okay, I heard negative, that is correct, okay? Because when you have a negative number and you have another number that is non-negative, if you compare two negative numbers, it's not going to have any problem. If you compare a negative number with a non-negative number, then we start to have issues, okay? So that means, whatever PA points to and whatever PB points to, one has to be a negative number, the other one has to be a non-negative number. If they have the same sign, then the problem won't show up. Okay? All right. But there's one case where the problem should show up too, is when it's 0. When both are when both have the same value, it will still do the wrong thing. But that's when it does the wrong thing. If you want it to do the right thing, you just have to make sure that whatever PA points to and whatever PB points to have exactly the same sign. They can both be positive, they can both be non-negative. It's okay. All right? But that's not the only problem with this code. There's some additional problem here. If you look at the swap code here, which is from here down to here, it has a little problem by itself. What are we actually swapping? Do we see any indirect operands from here to here? Let me choose a different color. So look at this code here. Do you see any indirect operand, which is basically just parentheses surrounding a register other than EBP? No, we don't have any dereference. We don't have any indirect operand here. If there are no indirect operand here, and it does seem like it's exchanging something, right? We are copying, okay, if you look at the first two lines, we are copying PA to T. The next two lines will copy PB to PA. The third line copies T back to PB. We are swapping something, but not what PA and PB points to. We are swapping what?
Their addresses.
We're swapping the pointers themselves. Would that do anything to what the pointers point to? Absolutely nothing. So that's the other problem with this code is it's not swapping what the pointer points to, it's only swapping the pointers. Okay, at the exit point of the subroutine, what happens to the parameters? They get recycled, right? You know, we don't keep them around. So that means this code doesn't do anything like what the C code is supposed to be doing. So there's no actual exchange or swapping happening. Is that okay? So we have two problems with this program. So you kind of have to spot those things. So to answer the question, identify a case where this code works correctly. We need X and Y to be different, but of the same sign. As long as it meets that requirement, it's going to be okay. So we'll say that, let's say X is 5 and Y is 4, okay? It's going to work correctly. In this case, it will exchange because X is greater than Y. So the end result, oh, I take it back. Nope, this is wrong. 4 and 5. Okay. In this case, the end result is nothing will be swapped because that's the actual logic of the code. It branches around the swap code, and the return value of the subroutine is a 0 to indicate no swap should have happened. Are we doing okay so far with this code? Okay. So this will work where the code does seem to work correctly. Identify a case where this code does not work correctly because the return value Z is incorrect, but the result values of X and Y are correct. Okay. So you have to be careful because it's very specific that I just want the return value itself to be incorrect, but I want X and Y to end up with the correct value. Well, there's one easy test case. If X and Y are exactly the same, it's going to be a problem that will fit exactly this description. Okay? So we'll have, doesn't matter what it is, we can have 0 and 0 here to make it simple. Because if you have X and Y being 0 and 0, the end result is going to be 0 and 0 anyway. Whether it swaps or not, we'll still end up with 0 and 0. What about Z? It'll be a 1, because the JB is not going to branch. If JB is not going to branch, that means we will go through the code that do the exchange, the swapping, and we'll put a 1 into T as the return value. And as a result, Z is going to be a 1, which is the incorrect part of this. Now let's double check. I just did not see. Okay, yep, we do put a 1 into EAX here, which is the return value. Okay, so this is the correct answer. Let me give you another alternative answer, and you guys tell me why it is not the right answer. Okay, so I'm going to put a I'll put a -1 here, and then put a 0 here. Okay. All right. So if X is -1 and Y is 0, what would be the outcome? Well, this is still going to be a -1. This is still going to be a 0. What about the return value?
0, 0.
Would it be a 0?
It doesn't branch.
Actually, this will actually be another correct result. Because the it is not supposed to exchange, but it will go through the swap. Or would it? No, this would not go through the swap. Let's see. Because -1 is the maximum unsigned value. It is actually greater than 0. It will go through the swap operation, so you will still end up with a 1 here. So this is the other case where the result seems to be correct, but it is actually not correct. No, I take it back. This is the case where X and Y ends up with the value that they're supposed to have, but the return value is incorrect. So what you want to do, I know we're running out of time, so what you want to do is to figure out the case where the results of x and y are both incorrect along with the value of z. See if you can make that happen. In other words, the exchange is supposed to happen, and it didn't happen.
The exchange should have become x and y.
Right. Alrighty. So I'll be over at the lab if you guys want to study or do some more work with the practice test.